Unfortunately, this is not the video that I wanted to be making today, but I haven't really gotten to the slides that I need to make for the next video. In the next video, we're going to be going more over the cosmos. I'm going to explain it in a little bit better way, maybe that people will be better able to visualize. These things are complicated when you're thinking about, the way that spherical geometry works. Or spherical trigonometry, and you're thinking about the way that what we see was applied to that and how you could apply that to a flat surface. It is very difficult to wrap your head around. I've been thinking about these things for years, so it's not something that you can just think about and be like, oh, okay, I get it. But some people can, but some people, it takes a while to wrap your head around the concept. Most people don't even know how the sphere works. Right, because they're in one location. Usually people don't look at the sky. They don't know about astronomy. They don't know where the sun and moon are in relation to each other, and the planets and the ecliptic and the celestial equator, all of those things. The general person isn't going to really know a lot about. So you've got to first wrap your head around the spherical aspect of it before you can wrap your head around a model that works based on that observation. And that is the observation that has been touted by the scientific establishment. So I don't do a lot of videos tearing that observation apart because my model works the same way, right? I believe in space travel. I believe in, the gravity, for instance. I think that all of these things that we can measure and that we can observe, it's a lot easier to come up with a different way they work than it is to just deny them. So we don't deny things that we can measure like gravity, but things work in a different way. And over the years, I've come up with a model, and it's a working model based on the biblical text, and it kind of draws a line between science and religion, between science and biblical cosmology, where you can say, okay, science makes these observations, so how can we take these observations and apply them to the biblical model? And it's funny, when you start reading through the biblical model in Enoch, all of these questions are answered for you. All of these questions that I had written down about what was wrong with the flat earth model were all one by one by one by one revealed out of the book of Enoch and out of the Bible. So it's a fascinating journey that I'm on, and today we're going to be talking about the globe, and we're going to be talking about how earth curvature is measured and why I believe that earth curvature is measured the wrong way. So if we're thinking about earth curvature, it's based on the tangent of the line of sight of the observer. So if I'm standing here as the observer, depending on what altitude I am, it's based on the tangent line to the edge, right? So this line, if I were to dig through the center of the earth, this line is 3,959 miles. Okay? So to the center, if I'm thinking about where the equator is, to the center is 3,959 miles. Across the surface is 6,225 miles, right? That's why, because it's a circle, that's why we need pi to calculate the circle based on the radius. But I don't need pi once I have the circle determined. And to make things easier today, we're just going to be considering a 360-degree track around an equator on an equally divided spherical Earth. And if it's a perfect sphere, you can really draw an equator around the Earth anywhere, right? I mean, as long as it equally divides the Earth in half. But that is the only place on a sphere that you can travel in a straight line and end up back where you were. If you try to travel in a straight line at 45 degrees, you're going to have to continually turn around the North Pole. And you can prove this by just looking down on a globe. Look down on a globe from the North Pole and look at the circle at 45 degrees. That is a much smaller circle, which means if I'm traveling across the surface on that circle, I'm going to have to turn the wheel. I'm going to have to turn that wheel around that circle, around that North Pole at 45 degrees. On the equator, though, I can just travel in a straight line without having to turn the wheel. And that's why we're going to use the equator. We're going to use the widest circle that you can take on the Earth in a straight line without having to turn the wheel at all. So if you took that circle and you stretched it out into a straight line, it would be a straight line that's 24,901 miles long on the equator. It would be a straight line if you unwrapped it from north to south. That's 24,860 miles around the poles. So not just from here to here, but all the way around, right? So if I'm traveling here and I'm going all the way around in this direction, I can travel in a straight, perfectly straight line on the water, provided that I am traveling on an equator, providing that I'm not leaving or deviating that perfect circle line. So again, to simplify, we're going to be thinking about the perfect circle around the equator. And one of the first arguments that I know I'm going to hear is Earth is not a perfect circle, it's an oblate spheroid. Okay, and we need to use spherical trigonometry. We need to use all of this, spherical understanding to understand the circle that's traveling around a sphere. But that's not true at the equator, right? If I'm at the equator, it is a circle. And because I'm traveling in a straight line at the equator and up is up, I'm held down by gravity. If I were to unravel that, it would be a perfectly straight line from here to there. That would reset on the other side based on our observation, based on what we see. But if I'm calculating from here to there, based on what the observer can see, there's a drop that is getting much more substantial the further I look, right? And we can only look so far. Like we can look like right here, right? Not like way out here. But this is wrong. And the reason why it's wrong is because it's not considering the shape of the degree. It's not considering where you're standing as the observer and how the degree is shaped in both directions, right? Because if I center a degree at the top, so if we turn this around a little bit, and I center one of these degrees at the top where the North Pole is, it's not just curving in one direction. It's curving here and it's curving here. So if I'm considering the shape of this, I need to consider the entire shape. I need to consider the entire sphere or the entire circle that I'm traveling. And if I do that and I break this down, it becomes a much more substantial curve. So the way that I'm visualizing this, and I believe this is the right way to visualize it, is if you're considering the curve along the entire surface, you can't just consider from here to here because you're only curving from here to here. But the Earth curves around back in on itself. And it curves around again, back in on itself. And again, back in on itself. So based on the tangent, I wouldn't only measure based on this tangent. I would also measure based on this tangent. And based on this tangent. And based on this tangent. So if I do that, it gives me a complete picture of that circle that I'm traveling on, right? And if I have a complete picture of the circle, very simply, it's 24,901 miles across the surface all the way around and 15,836 miles of drop around the center. Okay, so what do I mean by that? Well, if I take off in a boat or in a plane and I'm traveling to the equator, I'm not traveling in a straight line to the equator. I am on a globe. I'm definitely traveling in a straight line, but my straight line is moving in two directions, right? I'm moving this way and I'm also dropping. I'm also moving in an area or in a way that is curving down in front of me so that I can drop the necessary distance, which is 3,959 miles to the center of the Earth to the equator. Well, it's an additional 3,959 miles to the South Pole. And it's an additional 3,959 miles to the equator on the other side. And then to finish back up where you started, you need to travel an additional 3,959 miles, right? This makes it really easy because we already know the circle. We already know the size of the circle. Let me make that bigger. Scoot it back a little bit. Didn't realize the whole thing wasn't in there. All right, that looks better. So if we're considering the circle, which we already know the circumference of, and we break the circle up into 360 degrees like we have here, what is the difference between this degree here and this degree here and this degree here, this degree here, this degree here. What's the difference as far as the way they're shaped and the way I'm dropping around the center? Because if I'm standing here under like between 30 and 31, well, I've got to roll that back around to get the right perspective because I'm standing on top of it, right? We've got to remember gravity. Oh, there's my little flat earth. You got to remember gravity. Okay, so if gravity is being applied and I'm thinking about standing at 30 degrees, I would rotate that to the top based on my perspective, right? So I'm always looking down from every direction. If I'm standing at 10 degrees, I've got to rotate that around to the top. This is a little bit large, I can't turn it because I can't reach it right now. But yeah, so if I were to take this, let's do a simple math problem. If I have to travel 24,901 miles across the surface to get back to here, and I consider the center with a cord, so let's pretend it's a tether ball. As the tether ball is traveling in a straight line, it's moving down, right? And it's still moving down. And it's still moving down because I'm always at the top based on gravity. And it's still moving down. So the total distance that I'm moving down as I'm traveling in a straight line is 15,836 miles to get back to the North Pole, over 24,901 miles. So if I consider that every degree is exactly the same and it's oriented exactly the same way, how much is the drop for every degree? Right? So if I'm traveling across the surface over 1 degree and every degree is the same, and there's 15,836 miles of drop around that center of the tether ball, right? If you imagine it swinging around and it's attached at the center, that circle is 15,836 miles down and around, but the circumference of that circle is 24,901 miles. That is the correct way to calculate Earth curvature. And it's a paradox, right? Because it's crazy when you try to think about it. And I haven't ever had anybody be able to explain why this is not the way that you would calculate it in a way that I can't immediately overturn by the circle of the equator that we're traveling on. That's what a lot of people don't consider. Their first argument isn't considering the example that we're giving is traveling on the equator of Earth in a complete circumnavigation. And if I do that in a complete circumnavigation, 24,901 or 24,860 miles on the surface, I'm dropping around that center on the surface by 15,836 miles, which is exactly 43.9 miles for every single degree around 360 degrees. What is 360 times 43.9? 15,836, right? If this degree is the same as this and this and this, they don't change, right? The shape is not changing. And the way you can visualize the drop, if you're visualizing traveling east or west or north or south horizontally, you want to put your observer at the top. But if you want to imagine the drop for every degree, you put your observer at the side. And as you rotate that protractor around, oops, wrong way. As you rotate this around, if I'm here, right, that is how much drop there is for that degree. And it can't work any other way when you consider the entire surface of Earth. So what is more likely, what is more probable on a sphere to be the proper estimation for what the curvature should be? Is it to consider a fourth of the shape, especially considering that it actually curves back around to the axis, right? We have an axis running through the middle of this. So we're not just curving in this direction and falling straight down. We're curving in this direction and we're coming back around. And we're coming back around and we're coming back around. I know I'm repeating myself, but you have to repeat yourself sometimes for things to really get through to people, because like I said, these things are complex, and if you're visualizing it based on a ball and based on a solar system, you know, orbiting around the ball, you can visualize it. You can make it make sense. But when you really start to think about it and you learn the equations and you learn what we see, I mean, remember, based on that equation, the Earth would drop off like a cliff in every direction around me. Maybe not like a cliff, but it would be substantial. I would be able to see very far, right? And I want us to think about that. Think about standing here on a sphere and looking at this tangential line of sight. What am I doing? I'm looking higher in the atmosphere as I look through a straight line, right? So I'm looking through higher portions of the atmosphere, which means I would be able to see a long way. Because even if I'm looking down over that curvature, I'm looking down from a higher vantage point, right? From my perspective, because gravity is always going to put me in the center at the top. So it doesn't matter whether I go this way or this way or this way or that way. I'm going to always be at the top of the sphere. As I travel, my orientation is going to place itself at the top, meaning every direction is down. If I'm standing here, every direction is down. If I'm standing here, every direction is down. Here, every direction is down. Here, every direction is down. Every direction is up, 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 up. So when we consider what we would see, what we observe is what we observe on a flat Earth. And it makes more sense on a flat Earth. People say, well, if you're living on a flat Earth, you would see forever. No, you wouldn't. That's not even accurate. Because on a flat Earth, I'm looking through the densest layer of the atmosphere across a flat surface. And because I'm looking through the densest layer of the atmosphere, that atmosphere is going to obscure things over distance. Just considering water vapor, not considering dust, not considering gas, not considering anything else, just water vapor. Water is 784 times more dense in solid form, not solid, not ice, but water form, than the atmosphere. So a cup of water is 784 times more dense than the air that's around you. And if I can't see photons 1,000 meters below the surface of the ocean, the air over distance is going to do the same thing. It's going to block those photons over distance. And depending on how you work out that equation, depends on how much of that light you're going to see over distance. But the atmosphere on a flat surface is going to be much more dense at the surface, right? And a sphere will also be dense at the surface, but when you consider the tangent of my line of sight looking straight out in front of me, everything would be dropping down and around in front of me in every direction because of the shade. And when we consider where the horizon is put on this sphere, because we calculate it looking in one direction to here, right? When you do that, you end up with a very narrow view of the sky, because this tangent is what it is. If I'm standing on the North Pole out in the middle of the ocean in a little rowboat and I'm looking at the sky in every direction, if I'm looking at the horizon, I'm seeing stars that are here, right? But look at this tangent. Look at the line. My line is here. And the globe model explains this, and they have a semi-valid explanation, that the stars are so far away in this direction, that slight angle from that 3.14 mile horizon is going to meet perfectly at the equator, right? The problem with this is if we think about where it would meet at the equator, let's do a sharper angle, right? So let's say the stars are light years away, and over time, that angle is meeting the stars right at the celestial equator. But the stars are at different distances along the celestial equator. Some of them are here. Some of them are way out here. Some of them are way, way, way out here. And when we see all of these stars in the heliocentric model, because they're different distances, let's continue to think about it. If I'm looking in this direction, am I going to see stars directly above the equator? Or am I going to see stars way down here at this angle from the equator because of how far away the stars are? So, no, it doesn't really make sense. And that's the thing. People will say, well, you've got to have the math. The math works. The math works. Equations work on paper. And if you can convince people that the equation you're seeing on paper matches what they see in storybooks and cartoons, and you can do that from the age of 5, people are going to believe it. They're going to believe it. They're never going to question it. This is the most difficult thing to overcome with cognitive dissonance. I know, I've been there. Right? My friend introduced me to this, and it blew my mind. Because I've been there. I've experienced it. I've experienced that initial rage. Like, how can you be so dumb? Right? I know how you feel. It is. That's the initial reaction. It's like, why are you so stupid, Flurf? And that was my reaction. But I started to think about it because I really believe the scripture, and I always have. I believe it's a lot more literal than what people think it is. And I remember being a little kid and thinking about these things and looking at the weather map on TV and thinking in my mind, well, what if the earth just kind of reset in every direction? Right? I remember having these thoughts. I remember thinking in the Bible that says the sun was made on the 4th day. That's stupid. That doesn't make sense. It really bothered me as a kid. And it's because I had my brain as a child wrapped around the heliocentric model. Wrapped around that in the heliocentric model, the sun had to come before the earth. Right? And in the back of my mind, I was thinking the sun made the earth. Because why would the sun be here before the earth if it didn't make the earth? And if the heliocentric model is true, it's true. And earth came from the accretion disk around the sun. Earth wasn't made by God in the heliocentric model. So why in the heck does the church accept the heliocentric model? It makes absolutely no sense. The heliocentric model is the Big Bang. The heliocentric model is evolution. If you remove the heliocentric model and you go back to the biblical model, the Big Bang and evolution are stupid because the only option is God. And the microevolution that we see, or the mutations that we see taking place around us, they're obviously a part of the genetic code, right? We're able to, with technology, manipulate that code. Imagine what God can do. Imagine where God is. Imagine how much higher God's ways are than our ways, and that is the point of the argument that I'm making. And I believe that the observation with Earth curvature and what it would be like to live on a sphere the size of the Earth should consider the entire sphere and every degree so that we can come up with an accurate shape and what the drop would be for every degree around the surface. Right? It's kind of a paradox because when you look at it one way, it makes sense. Right? It makes sense to measure it this way from the observer's perspective. But when you're thinking about traveling, it makes sense to consider the entire surface. And then when you think about it, it's like, well, that doesn't even match at all. That's not even close, right? When you consider the drop around the center compared to what it would be predicted by this, right? If you consider the entire surface, that drop is much more substantial because you're always going down around this center. Every mile you're going down, 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 down. And if you only look this way, you're not considering that. You're not considering that down is a full circle of 15,836 miles. And if you do, Earth curvature completely changes. And we can see that we're living on a flat Earth.